Welcome back. In the next part of this section, we're going to talk about points of inflection. These are points where on our graph we are changing concavity from concave up to concave down or from concave down to concave up. But we need to be a little bit more precise here. For you to be a point of inflection, we need a few things. Number one, our function needs to be continuous on some interval containing our point of inflection. So in other words, our function needs to be defined at our point of inflection. We also need to have some kind of a tangent line and also to change our concavity in order to be a point of inflection. So a couple of things though. Having a tangent line does not necessarily mean that the derivative exists. Remember, derivatives exist when we have a tangent line that's not vertical, but of course you can still have a tangent line and the tangent line could be vertical. It just means that the derivative wouldn't happen to exist at that point. But we need the function itself to exist. So if we circle back to the last example that we have two places where it looks like concavity is changing at 2/3 and also -2. From our last example, we found that there were two potential places where concavity changes. But we had to keep in mind for ourselves that -2 for this function was a place where we had a vertical asymptote. Our function was not defined at x equals -2. So I would not be able to say that there is a point of inflection at -2. I would be able to say, however, since 2/3 is inside of my function's domain, and since f prime of 2/3 exists, I know that there's definitely a tangent line at 2/3, and I know that at 2/3 we're changing from concave downward to concave upward, so 2/3 would be a point of inflection for that last example that we did. So this is the other thing to be careful about is, again, thinking about needing to have a tangent line as meaning that we have a derivative, and of course that's not necessarily true. If you know the graph of y equals cube root of x, you can sort of see that, yeah, it looks like there's a point of inflection here at 0. And in fact, if you did the derivative, you'd find that for x equals, y equals x to the 1/3, that the derivative is 1/3 x to the 2/3. That's for sure not defined when x is 0. In other words, we've got a vertical tangent line, but we still have a tangent line, so I would be able to say that 0, 0 is a point of inflection on our graph. Needing a tangent line means that there's lots of places where we couldn't have a change in concavity, and that's any place that's a sharp corner, so something like the y equals absolute value of x. At that point, we know that there's no derivative, and there's no derivative because there's no tangent line, not because we've got a vertical slope. So for something like that, at a sharp corner, that would be a place where you couldn't have a tangent line, so that would be a place there where you don't have a point of inflection. So a couple of things we can say. We've got a nice little theorem here that tells us if you have a point of inflection, then one of two things needs to be happening. Either your second derivative needs to be 0, or your second derivative doesn't exist. The reverse is not true, though. If you have a place where the second derivative is 0 or does not exist, that doesn't necessarily mean that you've got yourself a point of inflection. It's possible that your second derivative could be 0 and you happen to have a minimum there, or you've got a maximum there, or something else going on. So, for example, if you're thinking about the graph of y equals x to the 4, that looks pretty much the same as y equals x squared. It's a little flatter on the bottom, but it's basically a parabola kind of a shape, and it's definitely concave up everywhere. It's not changing concavity from concave up to concave down, but if you did the second derivative, you'd find it's 12x squared, and that second derivative is 0. So here, that second derivative being 0 is not because we're changing from one kind of concavity to another. It's just simply because we happen to have a second derivative of 0, and that's just life, unfortunately. Things are not always going to be nice and work in both directions as far as theorems go. So if you know something's a point of inflection, then you know something about that second derivative, but the reverse is not true. If you just know that the second derivative is 0 or doesn't exist, that doesn't give you necessarily a point of inflection. So let's take a look at this function, sine plus cosine, and we want to think about concavity of our graph on that interval. So let's start off with this. First, let's find all of our possible places where we could have points of inflection, and then we'll test to see which ones of them are points of inflection. First, before I get into doing my derivatives, I'm looking at my function f of x, and I can see it's made out of sine and cosine added together. Sine is defined for all real numbers, so is cosine. There are no places where f would be undefined, so we don't have any discontinuities to worry about, so that makes life kind of nice for us. I'm going to just take a look at my first derivative. Derivative of sine is cosine. Derivative of cosine is negative sine. And then I'll take the second derivative. Derivative of cosine is negative sine. Derivative of sine is cosine. Okay, so now we're good to go. We're ready to start thinking about finding possible places where we could have our change in concavity. And if you had a point of inflection, then your second derivative would have to either be 0 or be undefined. This is defined everywhere. So I have no places where f double prime doesn't exist, so I guess I need to find out where is it equal to 0. So I have where minus sine x minus cos x equals 0. Or in other words, where minus sine x equals cosine of x, or where tangent is equal to -1. I don't have to worry, by the way, about losing any solutions here. You'll notice I divided both sides by cosine. So normally you'd have to worry about potentially losing solutions of when cosine is equal to 0. But we know when cosine is equal to 0. That's at pi over 2 and 3 pi over 2. And neither of those values happen to make this equation equal to 0. So I didn't lose any solutions. I feel pretty good about that. And now I just need to solve and find out when is tangent of x equal to 1. And I know that there's two places where tangent is equal to 1. One of them is at 3 pi over 4, and then the other one happens to be at 7 pi over 4. So there's those two places. There's in quadrant 2, and then there's also in quadrant 4. Okay, so I've got two things to test now. I have two potential points of inflection, and I guess I'm going to need some test points, and we'll need to find out what happens to our derivative at those test points. So the values that we'll put on our number line, I've got the 3 pi over 4. That's one place where my second derivative is 0. The other one is 7 pi over 4. And of course, I've got my endpoints. We're looking at this function going from 0 to 2 pi, so I will have to make sure that when I pick my test points, I pick something between 3 pi over 4 and 0, and I pick something between 7 pi over 4 and 2 pi. So let's get into this one. Let's start with between 0 and 3 pi over 4. Probably the easiest thing for me to select would be x being pi over 2. And so now if we're looking at our second derivative at pi over 2, you would have, since our second derivative is minus sine x minus cos x, you'd have minus sine of pi over 2, which is minus 1, minus cosine of pi over 2, which is 0. You'd have -1. That's a negative value, so we are definitely concave downward. Between 3 pi over 4 and 7 pi over 4, I guess pi is a good choice. Why not? So I'd have for my second derivative, I'd have minus sine of pi, which is 0, minus cosine of pi, which is negative 1. So my second derivative would be positive 1, positive, so we are concave upwards. And then between 7 pi over 4 and 2 pi, let's go for 11 pi over 6, 330 degrees. So for my second derivative at 11 pi over 6, we have negative sine of 11 pi over 6. Sine of 11 pi over 6 is negative a half. And cosine of 11 pi over 6 is root 3 over 2. And so I would get 1 minus root 3 all over 2, which if you were to put that into your calculator, you'd find that that's negative 0.36-ish. So that is a negative number. You are concave downward. So now I can say a couple of little things about this, and I'll make a little summary. So the first things first, our function was defined at 3 pi over 4 and 7 pi over 4, and that's because our function was defined everywhere, but in particular at those points. Our derivative exists at those points, so f prime exists at both of those, so we definitely have tangent lines happening at both of those places. And also we're changing concavity at both of those places. At 3 pi over 4, you're changing from concave down to concave up, and at 7 pi over 4 from concave up to concave down. So for my conclusion, we have a point of inflection at 3 pi over 4 and at 7 pi over 4.